Subr. Yes, so from this complicated title you may expect that I will not speak about gravitational waves actually, so it's true really. But what I will talk about are the dynamics in axially symmetric perturbed potentials, which may produce highly eccentric and tightly bound orbits, so it may be relevant for this audience, I hope. So brief outline, it seems to be short, but I will be happy if I catch it. So first, a few words about how to produce quasi oscillations and what they are. Then how to damp them, and it's quite realistic thing that they are damped by relativistic effects, for example. I will also consider a non-gravitational influence of some kinds of axisymmetric perturbations of the accretion disk on orbits of stars, which may be relevant. And if time and Chairman allows, I will try to say a few words about what funny things may happen if these both effects, the gravitational and hydrodynamical one, are considered both together. I was applying it for S-stars, but you can consider it as a channel of how to produce high eccentricity tightly bound stars. So first about the quasi. Especially Russian colleagues like to call it quasi-Lidov, as it was independently described by two persons for two different kinds of hierarchical triple systems. In these systems, the orbital elements of the particles, especially of the inner binary, secularly evolve in time. I'm not able to use it. And well, let's now skip to the last line. The method they use, the averaging technique for Hamiltonian perturbation theory, can be actually even more directly used also for a system when you have considered center mass and fixed axially symmetric perturbation. So I will consider these kind of systems actually, so not triple systems pure. And for these kind of perturbations or potentials, you can immediately see that there will be two integrals of motion energy, which is obvious. Z component of angular momentum, which I, for some historical reasons, denote with C1. And what is not that obvious is that, and what is the outcome of this averaging approach is that there is another third integral of motion, which then constrains somehow the oscillations. And this integral of motion is a bit non-trivial one. It's an average of the perturbing terms in the Hamiltonian with respect to the central Keplerian potential over one revolution of the orbit. So in this axially symmetric perturbation, if you have these two integrals of motion, you can easily, and it was already mentioned in this on this meeting, that you can have a polar orbit which is near a circular one, which can flip eventually to equatorial orbit, which is very eccentric. But it is these oscillations are somehow constrained by another integral of motion. So now I have a couple of slides with a sketch of proof of existence of this integral of motion. But if I go through them, then you should forget about coffee break, and I'm sure you would not like that. So we have to skip this fairy tale about beautiful equations and horrible singularities. Slowly. Okay. And I will stop here with figures. They are always better to read. So what I plot here? I plot here isocontours of this integral of motion. What do I fix in the figures? In all of them, the fixed quantity is semi-major axis, eccentricity, the energy, one of the integrals of motion. In each panel, I have different value of this Z component of angular momentum, but it is constant in each plot. I have two independent, rest-independent variables, eccentricity and argument of pericenter. Eccentricity is radial coordinate, argument of pericenter polar one. So for each point at this plot, I can it corresponds to a different Keplerian ellipse. Along this ellipse, I can simply calculate the average of the perturbing axially symmetric potential, which is now potential of a ring. And what I get is a function, two-dimensional surface, isocontours of this are these blue lines. The black lines are actually the same. They only try to emphasize this special separatrix, but the red lines are obtained in different way. They are obtained in such a way that I start integration of orbit in the compound potential, center one plus the ring, and I let it evolve over several thousands of revolutions. And at some time, I look what is the current eccentricity and argument of pericenter, and I plot these values here. And you see that this is the red line. It fits perfectly in these contours. So indeed, this is the integral of motion. It's the kind of proof. And from now on, we can consider these blue lines as a possible contours or tracks of orbit. How do they evolve in this space? So you can see that from actually starting from very small eccentricities, you can get extreme ones if you have sufficiently small value of that component of angular momentum. And the topology depends on this quantity. This is the same, but now the perturbation is due to an extended source. The difference, otherwise everything is the same, but difference, you see, there you can obtain a different topology, which can be interesting and may produce some funny effects in some cases. Now to the damping of quasi oscillations, which will naturally occur when you get close to the black hole, and this is also has been mentioned here. So relativistic pericenter advance damps this resonance. You can, for example, consider to compare characteristic times for these two effects. You can, by some analysis of the integrals of motion, get some minimum value of some major axis above which you will be able to reach some defined minimum pericenter due to quasi oscillations. If you get to smaller semi-major axis, the relativistic effect will be too strong and it will damp the oscillations, so you will not be able to reach the desired pericenter. How you can visualize this is to employ Paczynski beta potential. This is convenient for that. I can put it into a Hamiltonian, so I can split this Paczynski beta potential into two parts, a Keplerian one and some perturbation. I can add this perturbation to the axial symmetric one and plot again the contours of this sum, which is here. And you see that indeed, if I switch on GR now means Paczynski beta, so it's not exact, of course, but the Paczynski beta produces this pericenter advance to some level of accuracy. And you see that, especially in this left panels, that the contours are quite smeared and the oscillations, the possible oscillations are really damped, so you can go along the lines, and here the oscillations are much smaller than along these lines. This is for a ring. The message from this slide is meant to be that the disk resists more to the relativistic effect, but it does not mean that it makes it negligible. If you decrease the semi-major axis sufficiently, again, also the contours, the isocontour, this topology will be smeared, or even for a disk-like potential. But it resists more, and it can be important in some applications. Another damping can be due to precession, due to a stellar cusp, which I mimic in this case by smooth potentials, spherically symmetric with some power law radial profile. And now the contours, if I switch on again the relativistic effect, just to show how they change if I increase mass of this component. So first I have now this spherical component. You see this characteristic topology. It somehow changes if I add the numbers, simply some units. if I increase it even more, you see that actually I do not smear the topology. I even make it more complicated. But if I increase the mass too much, then a large fraction of the diagram will actually again consist of concentric nearly circles. So along these, no large oscillations do occur. But still, even if you are interested in eccentricities which are 0.9999, then still the loss cone may be considerably larger, as you here start from 0.9, reaching this desired value. So still, it may increase your loss cone or by a factor of 10 approximately, actually. So that's here. In this paper, which is submitted, we tried to consider how large fraction of stars from a given sample will reach center within a tidal radius. So we are not directly interested, for example, in gravitational waves, but it's at least a bit close problem. We employed a single parameter model. So what the model consists, it consists of a central mass black hole. It consists of a cluster which is scaled to its mass. It has the same mass. Its typical radius is derived from mass sigma ratio. The perturbing potential is considered to be a ring which is on the outer edge of that cluster. So everything is scaled to mass of the black hole, and actually what can eventually vary is the mass of the perturbation, which does matter. So here in these spots, all the lines are for the perturbation, which is 1/100th of mass of the central body. And now you can ask the fraction of stars with, for example, given same major axis, the cluster is considered to have this Buckle and Wolf profile, do reach center within the tidal radius. So the black lines are some analytic estimates. This is if I somehow estimate the efficiency of Kozai mechanism is 100%. Actually, it's 200%, but factor of 2 does not matter. This is if I simply calculate what fraction of the stars from or orbits from the given ensemble simply have pericenter closer to the center within this tidal radius. If I do not assume any evolution of the orbits. And you see, if you switch on a gravitational effect, GR effect, then you have this decrease of the fraction of stars around some value which actually corresponds to that estimate which I showed a few slides before. So the estimate seems to work quite well. And what happens if I even add the self-gravity in the sense of smooth gravity of the cluster itself? It's the blue line, and actually you see that the effect is quite stronger. And here it is as a dependence on the mass of the black hole. So this one was for, I think, our galaxy. So either it's 10 to 6 or 3 times 10 to 6 in this spot. So at least you can see that the efficiency of these of the Kozai mechanism, and actually even the fraction is larger, even if you do not consider Kozai. It's larger if you decrease the mass of the center source in this single parameter model, of course. For example, for galactic center, I have considered 2 kinds of perturbations. One can be this circumnuclear disk, which could produce about 1,000 up to 1,000 of stars reaching a tidal radius. Yes, so this is what I was doing today up to 2 o'clock. Actually, I was not calculating the data, but I was trying to understand what they are. A colleague of mine, it's a full GR. So you see in full GR, we are dealing with simple algebraic equations only. But actually, it's the GR does not much matter here. As the pericenter you see is about 600 gravitational radii here. But what I wanted to show, I have a code where there are which can which can integrate orbits of stars in a Schwarzschild plus some perturbations, which are actually exact solutions of vacuum Einstein equations. And as far as I know, there are plenty of these kinds of solutions for disk-like sources. So I think it is worth to be done, these integrations and comparisons with Newtonian or even post-Newtonian cases, as in that case you treat exactly also gravity of the perturbation, and some things are qualitatively exactly the same like in the Keplerian case here. I have decreased the mass of the perturbation and the period of the oscillations. Here is Carter constant, which is not constant in that case, of course, this function which will be constant in the pure Schwarzschild, and I don't know in which unit it is, but it oscillates and it somehow corresponds to eccentricity, of course, to the total angular momentum. The pericenter oscillates as the eccentricity oscillates. The period of oscillation here are different time scales. The time is in orbital periods. The period of oscillation is increased by a factor of 10 if you decrease by a factor of 10 the mass of the perturbing source, so that's fine. What is strange here, I was doing these playings some time ago and I don't understand it now. What is different in Newtonian case, I will never obtain, if I decrease the mass of the perturbation, I will not decrease a different behavior of the orbit, in the sense that here, from starting from some initial conditions which are the same here, I would not in one case get a decrease and so get closer, and in the other case only increase of the pericenter. So that's some qualitative difference which I don't know how important it is, and I think it is worth to be studied. So I have some time, so I really can call it only sub-conclusions which I put together. So I've written that AGNs, but actually also our galaxy contains these axisymmetric perturbations in the form of circumnuclear disk or a disk of coherently rotating stars, for example. So are these kinds of galactic nuclei likely to produce MRIs? Maybe they are, as you have this axisymmetric perturbation, which can be responsible for eccentricity oscillations, which is important to bring stars to this band. And the accretion disk may also cause energy dissipation, which I will have slide next. Another thing I would like to say is post-Newtonian corrections are important. If you wish to deal with resonant relaxation, with quasi-oscillations, you have to consider GR as the precession due to the relativistic precession interacts very strongly with this quasi-oscillation. So the codes which are willing to work with this stuff have to make some post-Newtonian corrections to the orbital evolution, which people here do, actually more of them. And as I've said, it may be interesting to study these oscillations in exact solution spacetimes. Another thing which I have a feeling is different is the boundary between chaos and regularity in these exact solutions. So that's another point which can be interesting for highly eccentric and tightly bound orbits. So now to the dissipative drag of the disk. That's a very simple model which is based on paper of Sir Clark and Rees, and it assumes that the stars from some cluster pass through accretion disk, and as the passage is supersonic, so you can treat it as an instant kick to the velocity of stars, which expels the material which lies on its trajectory. And actually, a parametric solution for such an evolution can be found. Having that's wrong. I again write C1, but it's not that C1 used before. Another two integrals of motion for orbital evolution. So you see that in this case, same major axis will decay, and eccentricity and inclination will also decay to the plane of the disk. In the late phase, you can find even some approximate temporal formula for temporal evolution. So the importance of this may be, as in order to get gravitational radiation sources, MRIs, you simply have to release energy from stars. You can do it by the gravitational waves themselves. You can do it by two-body relaxation, and you can also do it by some dissipation in a disk. What can happen if you consider both effects? So these are again these contours or perturbing potential in the case of disk-like source. And what can happen, not only that the star may oscillate along these blue lines from small to high eccentricity, but another channel how to produce high eccentricity star is even if you have these with small oscillations. Actually, there are more stars in this region typically than in these regions. You can produce high oscillations from them just if you kick them, push them through this separatrix by some process. It can be again actually a relaxation, two-body relaxation. It can be this drag of the disk. In that sense, the model is meant to be self-consistent, and from this, which oscillates only slightly, you can get orbit which oscillates up to really high eccentricities. And if you put it into the model of dissipative drag of the disk, then you have this kind of figure. So blue line now is dissipation due to the disk only in that non-gravitationally perturbed regime, so you do not have quasi-oscillations. And the red points are some snapshots of orbital evolution if you also consider this quasi-oscillation. So initially, you see that you have small oscillations, but as the evolution due to the drag of the disk proceeds, you can get to some kind of resonance where you cross this separatrix, you abruptly increase the eccentricity oscillations, the range where it oscillates. It then accelerates the orbital decay, so you can effectively produce tightly bound and highly eccentric orbits. And I think that's the last slide. Thank you. Well, it depends. I think what one should do, actually what I was doing when I was producing these kinds of figures, which are based on the integrations of many orbits, I did it in first PN. The Paczynski Vita was employed only for the graph, so that I have Hamiltonian. How it will alter it, the question is how is altered this pericenter shift in Kerr metric with respect to Schwarzschild. I don't know, but I guess that people do know. So. I think even if you are perfectly axisymmetric, you can have chaotic orbits. That statement that you have a third integral of motion is not strictly valid. So even in that case, you can have chaotic orbits which evolve more widely, and some moment they end in the singularity. I guess if you get rid of even this axial symmetry, this tendency will be stronger. So you will have probably a higher number of chaotic orbits which will have tendency to plunge into the singularity at some moment and probably will not be interesting, for example, for gravitational waves, is my guess.